I wanted to make this video to highlight a couple of items about the thermistors. We recall that the thermistors are devices that are very sensitive to temperature. So what I'm trying to do here is, here we go. We have our conductivity equation, so that we know that our conductivity is equal to the inverse of the resistivity. And with metals, what we see in terms of the temperature relationship is we see that the resistivity is essentially a linear function of temperature. So if we took, for example, the derivative of the resistivity with respect to temperature, we would get, some sort of constant value times, alpha. So this is essentially a material parameter, and this works for metals over a limited range of temperature. Limited temperature range. Now, thermistors, on the other hand, are very sensitive to temperature, which means they probably are not simply just linear with temperature. Well, what is the relationship for thermistors? Well, you recall, let me see, you recall that, that thermistors are largely made of semiconductors. Oh, I see that I somehow, here we go. Semiconductors, and the operative equation for semiconductors is that you usually look at conductivity rather than resistivity, but you can see that they're inversely related, and it's equal to the product of the charge of the carrier times the number of carriers per volume times the mobility of the carrier. Now I want to show you how this equation that was represented, for example, in Wikipedia. You'll see that, I'm going to get rid of this guy. You'll see that this, taken from Wikipedia, shows you that when they talk about thermistors and temperature relationships, they give you this Steinhart equation, which I think is always crazy, naming things after people, but anyway, so they give you this equation, and I'm going to tell you why I don't like this equation right here, is because this equation doesn't really tell you anything about what's happening inside the material. And my belief is that your equation should really support your understanding of the physical reality. And for me, this equation doesn't do it. So I have the same issue with the Schrodinger equation. Anyway, so what I want to do right now is to kind of take apart this equation a little bit and show you that if you look at, for example, this term in the equation, this is an empirical equation, and you can see that these are empirically derived coefficients, A, B, and C. And they're showing you that, look at the C value. This is 10 to the negative 8. So what they're basically telling you, the B value, the A value is 10 to the negative 3, B is on 10 to the negative 4, and this 10 to the negative 8. So you can tell that this term essentially is not that important. So let me just rearrange this equation. Now we're left with this. 1 over t equals these things over here. So what if we rearrange this equation to be 1 over t is, minus a equals b times the natural log of r. It's kind of sloppy here. Or, in other words, the natural log of r equals 1 over b times 1 over t minus a over b. And then I take this whole thing and okay, and then let's take the exponential of both sides. Raise this to exponential, and you'll see what you get is on this side, this turns into r equals, this side is exp negative, or excuse me, 1 over b times 1 over t times exp to the negative a, or exp of the negative ab. Now notice this is a constant. Okay, so what we have here is r equals a constant times e to the 1 over b, 1 over t. Okay, so for me, this equation right here doesn't mean anything. This doesn't really give you insight into what's going on with the with the device. And you recall that R equals rho times L over A. Not the device, but the material. And the material parameter is this one, resistivity. So I could kind of rearrange this. You can see here are the geometric factors, and those would probably go into the constant. So I could rearrange this to this form. Rho is equal to rho is equal to some constant, some prime, times e to the 1 over b times 1 over t. Okay, so here's our new equation, but once again, this doesn't tell me much. So what you often see in books is something more like this. Conductivity is equal to some constant, conductivity naught, times e to the minus e gap over 2 kt. Okay, now this is for an intrinsic semiconductor, which means one that is not doped. So for me, what I like about this form of the equation is that here you kind of get a sense about what is controlling the conductivity. So we can see here that, or a way to break this down is to actually say, okay, up in this term right here, that the conductivity is, okay, if we break this out, E gap is somewhat of a barrier. As E gap gets larger, you can see that this term gets smaller under the same conditions. 2 kT, this may be familiar to you. This is essentially, this is the internal energy available to overcome the barrier. So if there's more thermal energy or internal energy, it's easier to overcome this gap, and the conductivity goes up. So I like this form of the equation more, and you can see that it comes out of this guy. Oops. I guess I can't move that. So it comes out of this form. Conductivity is 1 over resistivity. You can see that these are inversely. I've just the exponential has gone negative, so it's just kind of a rewriting of this equation. So again, I like this form more because to me it tells you more about the physical conditions. And I want to point something out too of the form of this. Let's just really quickly go look at probability. So I'm going to try to go to a website here and search on the term. So this Wikipedia page is from the Arrhenius relationship, which you've seen in chemistry. And the thing I wanted to point out is the fact that this equation is almost identical. In fact, it is identical in form. You have a constant. So this is the activation, the rate constant is chemically activated equals some constant times e to the minus EA, activation energy, over RT. So I'm just pointing out that the form of this equation, a thermally activated process, is equal to a constant times this term right here, which is essentially the probability that whatever's going on will be accomplished. So if we go back to, boy, I don't know if I can do that. Hold on. If we go back to this slide, we see the same form, that the conductivity is some constant times this term, e to the minus activation energy over the internal energy that's available. So the generic form of this equation, just to be clear, is that the rate of an event, okay, in this case, the rate that you would produce charge carriers, intrinsic charge carriers, is equal to some constant, and this has to do with, you know, the availability of attempts times the probability that you'll overcome some barrier. And in this case, you could see that the probability of overcoming the barrier goes up if the barrier is higher, and goes down if the internal energy available to overcome it is greater. Okay, so that term goes in there. All right, I hope this is helpful.